Class recording for today has begun. So don't say anything dumb. So, all right. I should probably take this out. All right, over the past couple days, we've been discussing this idea of projectile motion, and like we discussed on several occasions, projectile motion is the motion of objects moving in 2 dimensions under the influence of gravity. And we said that the big key is that the horizontal motion does not affect the vertical motion. They occur simultaneously, but they are independent of one another. And because of that, when we are analyzing projectile motion, right, we talked about, got my pen, got it though, it's okay. We talked about the idea that when we are analyzing projectile motion, we have to analyze the horizontal and the vertical separately from one another. Because even though they both happen at the same time, they are independent. But we said because they are both happening at the same time, if we can either calculate or measure the time of flight, that has to be the same because they are happening at the same time. Then at the end of class yesterday, we were talking about the idea that if we want to talk about some factor or some measurement of the motion at any particular moment in time, like problem or letter C yesterday, where we talked about the velocity just before this arrow strikes the ground, we have to take into account both the horizontal and the vertical component of that motion, because we can't isolate one or the other. They're both happening at the same time. And that got us into a discussion about the vector sum, or the resultant vector of 2 perpendicular vectors. We are adding these vectors together, right? Using this plane as an example again, right? If we go northeast, we are adding the north motion of the plane and the easterly motion of the plane to get the resultant northeasterly motion. But when we add vectors together, it's not as easy as just adding the numbers. 300 isn't just 150 plus 150. That's not the way it works. We call in our right angle trig stuff, Pythagorean theorem, sine, cosine, tangent, and we'll talk about those a little bit more today, to get that resultant vector, and that's how we add vectors in 2 dimensions. Okay? In 1 dimension, it's just either adding or subtracting, depending on which way they're going, but in 2 dimensions, we have to call in some right angle trig stuff. Okay? Good there? So, for example, right, this arrow problem that we did yesterday was an example of one kind of projectile motion that we refer to as a horizontal launch problem. And in your book, also, oh, I thought I put it on there. Apparently not. Sorry for breaking the flow. No, apparently I didn't. Well, let's go with this one. All right, so this problem that we did yesterday from your book on page 43, it tells you specifically that this arrow is fired horizontally, right? That when it becomes a projectile, it was moving horizontal, just like in this picture right here. And we said that that's important when we are figuring out or determining factors of that motion in our chart of horizontal and vertical motion, because it means that the initial horizontal velocity, the initial vertical velocity is 0. If we shoot that thing directly horizontally, at the moment gravity takes hold of it, or the moment gravity starts affecting it, it's not going vertically at all, only horizontally. It immediately starts going vertical, downward, but at that very instant when it becomes a projectile, the initial velocity is 0. Okay? Good there? All right. Austin, will you do something for me? Will you turn off the bottom 2 lights? So, in the wintertime, when it's not quite winter yet, but it's kind of dark outside. So there we go. All right. Good there? All right. Today, we're going to do a different type of problem that we refer to as not horizontal launch, angle launch, and it begins with this problem right here. So it says, this is the first problem on the sheet that I gave you today. It says, a soccer ball is kicked from the ground with an initial speed of 12 meters per second at an angle of 32 degrees above the horizontal. What are the x and y positions of the ball 0.5 seconds after it is kicked? Okay? Good there? All right. Because this is the first type of problem, let's start off. Oops. I'm just adding an extra page in here so I can draw on some things. Okay. Because this is a new type of problem, I'm going to start with a picture. All right? So here, ground. Okay? Person getting ready to kick a soccer ball, okay? And it tells us a little bit about this soccer ball when it's kicked. It says it's kicked from the ground with an initial speed of 12 meters per second at an angle of 32 degrees above the horizontal. This is probably a little more traditionally what you might think of as a projectile, right? Starting off, okay, it says, goodness gracious, backwards arrow, you guys couldn't see that, but, go this one, okay, not to scale, because the way that I drew it, I'm drawing it for effect. So it says that it's kicked at 12 meters per second, and that it's kicked at an angle of 32 degrees above the horizontal. Okay? That's what the beginning of this problem looks like. Now, will the soccer ball ever follow this path that it was initially kicked? No. As soon as it leaves this guy's foot, what starts affecting it? Gravity. Gravity will never allow it to follow this path. It will immediately start pulling it downward. But, just like we did when we threw the ball up in the air and it came back down, and we talked about it slows down and it speeds up, that happens here as well. But while it's slowing down on the way up and speeding up on the way down, what is it also doing? It's still going to be doing what while it slows down on the way up and speeds up on the way down? Yeah, I think I jumped a step. Hold on a second. Okay. Let's go here. So here's where this problem becomes a little bit different. When it becomes a projectile, when it starts moving under the influence of gravity, it is not moving horizontally like that arrow was, right? It's moving in a direction, or it's moving with a speed of 12 meters per second at an angle 32 degrees off of the ground. The only way that this happens is just like the airplane. A speed of 12 meters per second at 32 degrees above the ground is a combination of a horizontal motion and a vertical motion occurring simultaneously. Does that make sense? Right? If we're going to go up and to the right at the same time, we got to go up and to the right. Okay? Meaning that in this problem, we can do this. That purple line is the resultant vector of an individual horizontal vector and an individual vertical vector. Does that make sense? The resultant motion up and to the right is a motion up and to the right. So if we can figure those two out, we can figure what's going on at the beginning of this problem. Because remember, even though the ball does go in a diagonal direction, the independence of the horizontal and vertical means that these two things are happening independent of one another. They both affect the motion of the objects, but they're going to happen independent of one another. Okay? Good there for starters? All right. So let's do this. All right. So we said that analyzing the motion of this soccer ball, sorry, now let's back up. Okay. This red arrow right here, an upwards component of velocity. If we had thrown a ball upwards, right, we know from the last unit that it slows down, comes to a rest up at the very, very top of its motion, and then it speeds back up when it comes on the way down. Yes? That all sound familiar? Okay. That will happen in this problem too, because of this red arrow component that we drawn on there. But the entire time that it's slowing down and speeding back up in the vertical dimension, what will continue to happen? It'll continue in the horizontal dimension, because remember, gravity is only affecting the vertical motion, not the horizontal motion. So this blue arrow will continue to move the ball forward as it's slowing down and speeding back up in the vertical dimension. Okay? Good there? As a result, like we discussed, it never follows this path, right? But it will follow a path that looks like that. Any guess on the shape? Now this one isn't a half a parabola. This is going to be a full parabola, right? It's upside down, but it's still a parabola, right? Okay. Good there? Okay. All right, so let's start analyzing this motion. Okay? ID and money. That's a good deal. So I hope somebody shows up and delivers me money too. All right, so let's start analyzing this problem. Okay, it says soccer ball is kicked from the ground. What are the x and y positions of the ball 0.50 seconds after it is kicked? Okay, if it's asking us for x and y positions, right? We're going to need a chart, just like we set up in the last problem, because we have a horizontal motion and a vertical motion occurring at the same time. So I'll set up a chart. So you've got down the middle, right? One side of the chart horizontal, one side of the chart vertical. Okay? Good there? All right. What is this question asking us for? X and Y positions, which would then turn into what, Austin? Displacement. So it's asking us actually for two unknowns here. Horizontal displacement and vertical displacement. Okay? All right. Good there? Let's start plugging in things we know. We said that there's one row of this chart we can fill in right away on every problem, no matter whether it's a horizontal launch, angle launch. It applies to every single projectile motion problem. What row is that? Acceleration, right? We said that the horizontal acceleration is always going to be what? Horizontal acceleration will be 0, because gravity is the only thing affecting it, and gravity affects things vertically. There's nothing horizontally. That means what's going to be the vertical acceleration? What's going to be the vertical acceleration? 9.81, because that's the acceleration of gravity here on Earth. In most cases, that 9.81 is going to be which direction? Negative, because we're going to go downward. Okay? All right. Other information they gave us in the problem. There's one other thing they gave us in the problem. What did they give us? They gave us a time, right? 0.5 seconds. What did we say had to be true about time? Time is the only row in this table that what has to be true? They have to be the same on both sides, right? So the time horizontally is going to be 0.50 seconds, but that's also going to be the time vertically because they are occurring at the same time. All right? Subot equations. How many pieces of information do we need to know in order to use them? We need to know 3. How many do we have right now? 2, right? Austin, go ahead. We can do velocity. Let's talk about this triangle that I drew at the very, very beginning of this problem, okay? This 12 meters per second at an angle of 32 degrees above the horizontal. Is that a horizontal velocity? No. Is it a vertical velocity? No. It is a resultant velocity, okay? It's the combination of the horizontal and vertical. But if we can figure out the horizontal and vertical contributions to that resultant velocity, we will know this square, or that spot, and this spot. If we can figure out the horizontal and vertical contributions to this 12 meters per second at 32 degrees, that gives us the initial velocity horizontal and the initial velocity vertical, because that was what's happening right at the moment that it becomes a projectile. At least good theory-wise with what we're doing here. Okay? Well, let's take this triangle. I'm not going to be able to move this, I bet. Oh, I can. Look at that. Oh, that's not going to work. All right. So here's this triangle. And, no. I'll just rewrite it. Let me take it up here. Okay. Here's the triangle. And we said that this is 12 meters per second, right? And this angle was 32 degrees. Can you guys see that? Because I'm writing it over the words. Okay. Just for clarity, I'll make this a little bigger. All right. And like we said, that resultant velocity is a combination of a horizontal motion and a vertical motion, right? Horizontal and vertical, x and y, are perpendicular to one another, which means the blue and the red form a right angle. And now we've made ourselves what? A triangle, but a specific kind of triangle, a right triangle, or right angle triangle. And we can use all of the fun trig identities that we learned back in Algebra 2 or wherever we learned. I can't remember what. All right, so here we said, though, that this is a velocity. This 12 meters per second is a velocity. And that means that the two sides of this triangle will also be velocities. That 12 meters per second occurs at the very beginning. It's the initial velocity. And that means that these two are initial velocities as well, but this is going to be our initial velocity horizontal, and this is going to be our initial velocity vertical. Does that make sense? Okay. So, which one do you want to do first, horizontal or vertical? Horizontal? Okay. So, the 12 meters per second is what side of the triangle? It's the hypotenuse of the triangle, right? The horizontal initial velocity will be which side of the triangle in relation to the angle that we know. It's the adjacent side of the triangle, right? Do we remember which trig function brings together adjacent and hypotenuse? Cosine, right? Okay, SOHCAHTOA, right? Do you guys know SOHCAHTOA? Some math teachers teach it that way, some math teachers don't, all right? So, remember that cosine of theta is equal to adjacent over hypotenuse. That's our definition of that's how we define cosine. Remember your trig functions, they're just relationships between different parts of a triangle. Okay? So in this case here, theta is 32 degrees, right? Because that's the angle that we know, right? We've already discussed that the adjacent side will be the initial horizontal velocity, u sub h, right? And then the hypotenuse of this triangle is 12. One thing you want to do in this part here, right? Make sure your calculator is in degrees instead of in radians, right? If you don't know how to do that, hit the mode button up in the top left, right next to seconds, right? And check and see if you're in degrees instead of radians. You'll probably have to switch back and forth between that and radians for math class, but it's just the way it goes sometimes, right? And we should get something less than 12, right? Because what do we know about the hypotenuse of the right triangle? It's always the biggest side, right? So we got to get something less than 12. What did we get? Anybody actually run it for you? 10.18? Okay. Oh, pen. All right, so this will be 10.18. All right, then u sub v, the vertical initial velocity, right? That's which side of the triangle in relation to the angle that we know. It's the opposite side of the triangle, right? It's the one across the triangle, okay? Now, you have a couple of options here, right? You know the hypotenuse of the triangle is 12. You know the adjacent side is 10.18 from your previous calculations. So you can actually go two ways with this to find the opposite side. I would recommend sticking with the information that the problem gave you, just in case you made a mistake when you calculated the adjacent side. So in this case here, I would go with sine. Sine is opposite over hypotenuse, right? That's how we relate the two sides of the triangle. Opposite and hypotenuse is through sine. So sine of 32 equals u sub v over 12. Now, not that I drew it this way, but this side of the triangle should be the smallest side of the triangle, because 32, right? When we're at 32, the opposite side is going to be less than the adjacent side. At 45, they're equal to each other, and then past 45, the adjacent side will be smaller and the opposite side will be bigger. So this one should be smaller than 10.18. Anybody run it through and get an answer? 6.35? 6.36? Okay. All right. Good there. Using our trig identities here. In this problem that we did yesterday at the end, we calculated the two sides of the triangle and found the resultant, or the hypotenuse. Okay? That's finding the instantaneous velocity. But in this problem here, it gave us information about the initial velocity. It gave us the hypotenuse, and then we had to use our trig identities to find the two sides of the triangle. But more importantly, to where we're headed with this problem, we said because that 12 is the initial velocity, the two sides of that triangle become the initial velocity horizontal and vertical. Okay? Good there? Now, how many pieces of information do we have in each column? 3. Now we can use our Suvat equations. Okay? Good there? All right. Use your Suvat equations and figure out what is the horizontal displacement and the vertical displacement. Go. So answers up on the board if you want to check and see how you're doing. I think they're right. All right, it's good there. We need a couple more seconds to finish up this calculation, and we got it. Those two sides of the triangle, the two legs of the triangle that we got from using the trig identities and the hypotenuse of the triangle here, the two sides of the triangle we refer to as the component vectors. Right? Those two sides of the triangle are the component vectors of that 12 meters per second. The component vectors are the two contributions horizontally and vertically to the resultant vector, which is the hypotenuse of that triangle. Okay? Good there? All right. Number 42 says, referring to problem number 41, what are the x and y components of the soccer ball's velocity 0.5 seconds after it is kicked? Well, kind of by process of elimination, what is this problem asking us for? Velocity, which velocity? Final velocity, right? Final velocity, but both x and y final velocity. Kind of by process of elimination, it's the only spot in the table that is still open, but whenever we talk about, right, velocity and after in the same problem, right, that's going to imply that we're looking at final velocity, okay? All right, so that means that we have two spots left in this table. What's this and what's this? One of them is super easy, okay? Which one's going to be super easy? Horizontal, right? What's the horizontal acceleration? What's the horizontal acceleration? 0. And if something isn't accelerating, what's true about its velocity? It's constant. So if the initial velocity is 10.18 meters per second, what's the horizontal final velocity going to be? 10.18, because it never changes. Oops, blue. Okay. So horizontal initial and final velocity always have to be the same because acceleration is 0. Okay? Now, vertical, though, becomes a little trickier, but we have so much information here, right? There's a ton of different ways that we can find it. I would probably recommend going with this one. Kind of the most simple equation. V is equal to U plus A times T. Okay. Did we get 1.45? Okay, so question. Has this ball reached the top yet? Devin says no. He's right. How do we know that the ball hasn't reached the top yet? Good. It's not negative, right? That vertical velocity is still positive, meaning that in the vertical dimension, it's still going upward, right? What would the vertical velocity be right there? What would the vertical velocity be right there? It should be 0. That was supposed to be the top of the motion, right? Now, the vertical velocity is 0, but does that mean the ball is at rest at that point? No, it's still doing what? Still moving horizontally, right? So at that point, the velocity would just be 10.18 because there is no vertical component. It's all horizontal at that point in time, okay? But the way this question is asked is probably not how I would ask it to you on the test. I wouldn't say, what are the x and y components of the ball's velocity 0.5 seconds after it was kicked? I would say, what is the soccer ball's velocity 0.5 seconds after it is kicked? Okay? Notice I wrote it in purple, right? Because if I want to know what the velocity is 0.5 seconds after it's kicked, what do I have to do? The velocity of the soccer ball is a combination of its horizontal and its vertical, right? Or, we gave it a name yesterday, we would have to find the what? The hypotenuse. We gave the hypotenuse a name yesterday. Do we remember what that name is? It's in your notes. It's in your slides if you watch the video. So, the hypotenuse of that triangle we refer to as the vector sum or the resultant vector, right? So, going back to this picture right here, okay, oh, nope, this one, okay. That's the top of the motion, right? That's not the one that we want though, right? I'm going to erase some things here. Okay. This is the beginning, so let's get rid of that because we're not worried about that anymore. Okay. And so, we said 0.5 seconds. We're still on the way up. It hasn't reached the top yet. Okay? But there we've calculated that it's going 10.18 this way and 1.45 that way. Yes? Because those are the final velocities 0.5 seconds after we kick it. Okay? Now, to find the actual velocity, we have to find the what? The hypotenuse. Even though these are actually not set up the right way, okay? We can move these around a little bit. Yeah, we could make a triangle out of this, but usually we set up our arrows to like go in order, like one ends, then the next one begins, right? So what I'll do here is take this red arrow. Oh, they all move at the same time. Not what I wanted. This is faster. So I'll just move this red arrow from here to here. It's still 1.45, but now it starts where the next one ends, or the previous one ends, sorry. And now I can find that hypotenuse, which will be the velocity at that point in time. Okay? Do it. So what am I going to do to find the velocity? Pythagorean theorem, right? Go ahead, do it. Unless you did it, did we do it already? 'Cause- so. All right. Good there? Good, take a sweaty. All right, good there? So here in this problem, right, the big difference being in this problem that we did yesterday with the arrow being shot off of the tower, it became a projectile with the horizontal launch, where the initial velocity in the vertical direction was equal to 0 because it was moving horizontally when it came under the influence of gravity. Today's problem, being launched at an angle, it's moving both horizontally and vertically when it becomes a projectile. We refer to these two as the component vectors of the original velocity, right? This would be, the 12 would be u, because that's the initial velocity of that object. But when we're analyzing the two-dimensional motions, we can't talk about the initial velocity. We have to talk about the horizontal initial velocity and the vertical initial velocity, which are the component vectors of the 12. We use sine and cosine to find those two sides of the triangle. Okay? Good there? All right. Homework on the calendar for tonight is very similar to problems like this. They're horizontal launch problems. Basically, you're still setting up your table, right? But to find the initial velocity, horizontal and vertical, you're going to use your trig identities to find the component vectors of the initial velocity. Okay? Good there? All right. Tomorrow, we'll do some actual measurements in class. We'll do some actual we'll actually shoot projectiles through the air. We'll take some measurements, and then we'll do some predictions based off of those measurements. Okay?